All right. Well, it is good to see everyone. I hope that you're having a good day and that you had a good weekend. A few things. If anybody's wanting to retake the integration quiz from last week, we have until Thursday morning to go ahead and do so. Coming up on Thursday, what is happening? We have our first exam of the 9 weeks. Yes, we want to be looking ahead to that. I'm going to go ahead and let you use your notes on that. It covers a lot of concepts from our calculus unit, but I also went ahead and put a chi-squared to test for independence problem on there because as of today, we are roughly 3.5 weeks out from your first paper exam. So if you have the opportunity, definitely go ahead and take a look at those reviews that I've been giving you. I just went ahead and gave you review 4, which is posted to your website. And if you take a look here, I've got the key already worked out for you. So we have a few lessons to take care of after we finish the calculus unit. So I'm actually really hoping right now that we'll have maybe a couple of weeks to spend just on review, the calculator, making sure that you're ready for the paper exams. Okay, so any questions about that? Okay, in fact, that's the only assessment we're going to have this week is on Thursday. We're going to start the trapezoidal rule today. If we can go ahead and get started with sinusoidal functions later in the week, that'd be fantastic. But we all know we have a long weekend coming up. Very, very much needed. We have Friday and Monday off, thank goodness. Before we go ahead and get started, though, here was the question that was on the board when you walked in. Would you rather be stuck outside in a dust storm or a thunderstorm? Thunderstorm has been the overwhelming response today. So why would that be? For obvious reasons, such as, wouldn't the rain be cold? Dirt would get in your eyes, okay? Okay. True. But don't you think living in West Texas here, we'd be like, you know what? Dust storm, that's just another day in Lubbock, Texas. Maybe tired of them? Okay. All right. Okay. All right. So any other ideas? No? Okay. Well, Mr. Gonzalez was very sorry that he couldn't be here today. In fact, starting today, for the rest of his time here, he is completely taken over. So he's not only taken over the pre-cal classes already, he would start teaching PSAT as well as IB. And he was really excited to get that started today, but unfortunately he wasn't feeling too good, so I went ahead and sent him home. Hopefully he'll feel better tomorrow and he's back. But when he does return, he is going to be teaching you. So we're looking forward to that. All right. Now, one thing I want to go ahead and do before we get started on the trapezoidal rules, I want to go ahead and talk about at least one of these. Did anybody have the opportunity to look at the optimization problems? Okay, these are really, really good problems to work on to see if you're understanding the idea about derivatives, finding the maximum and minimum values, all of that good stuff. Okay, so let's just start with number 1. Okay, number 1 says a can of dog food. So hopefully this problem is not going to be too rough. Oh, mercy. Okay, so a can of dog food contains 500 cubic centimeters of food. The manufacturer wants to receive the maximum, okay, there's a key word, okay, maximum profits by making sure that the surface area of the can has optimal dimensions. Let the radius of the can be r centimeters and the height be 8 centimeters. Find the dimensions of the can that will have the minimum surface area. Okay, so there's this word here, minimum surface area. Now, this problem is actually talking about 2 aspects when it comes to the can. What are they? One is surface area. The other is volume. Okay, so let's go ahead and write out these formulas real quick. So can anybody remind me, what's the volume of a cylinder? Pi r squared times h. Very good. Pi r squared h. Now let me go ahead and draw this. This is not going to be a good picture, but let's say I have a cylinder here. Okay. Well, the area of the base, of course, is going to be a circle. So the area of a circle is pi r squared. So here's the radius that we're talking about. And then, of course, we multiply that by the height of the can. So there's my volume. Okay. The other part of this is the surface area. Okay. Now, the surface area is actually going to have two parts to it. We have two circular ends. So the area of a circle is pi r squared, but we have two of them. So that's 2 pi r squared plus, now what I need is the area going around the can itself. So this is going to be found by taking 2 pi r times the height. Okay, would anybody like me to elaborate on where I got that? Like, what is 2 pi r to a circle? It's the circumference. It's the actual distance around the circle, like its perimeter. Okay, but we don't say perimeter, we say circumference. So here are my two formulas. Now, the best advice I can go ahead and give you on a problem like this, especially if they go ahead and talk about two different aspects of the problem like they did here, the volume and the surface area, you want to focus on the one that's asked in the question. Find the dimensions of the can that will have the minimum surface area. So it's the surface area portion that I need to work with. Okay. So what other information do they provide me? Oh, bless you. There was one other bit of information that we have. Ooh. The 500 represents what? The surface area or the volume? It represents the volume. So I'm going to come back down here, and I'm going to go ahead and replace the volume with the 500. Okay. Now, the surface area formula is the one that I want to go ahead and focus on. But you'll notice it has two variables. Now, we're trying to figure out what's the radius that's going to give me the minimum surface area, right? So I'm thinking that the radius is the one that I want to work with. So why don't we go ahead and take the first equation. Let's solve it for h. Okay. So all I want to do is isolate h. What would I divide by? Pi r squared. So I would get 500 divided by pi r squared, right? So I'm going to use substitution. I'm going to go ahead and take this expression that we just found, and I'm going to plug it into the other formula. Is everybody okay with that? Okay, so here's what I'm doing. Let's go ahead and plug it in, and let's simplify. So this is 2 pi r squared, that's a 2, plus 2 pi r times 500 over pi r squared. Okay. Now, what's going to happen when I substitute that in? Can I simplify anything? Well, it's a monomial, so when I multiply, something's going to happen. Like 2 pi r times 500 over pi r squared. Okay, so the pi's are going to cancel, right? Now, the r's won't completely cancel because I only have the one r, right? But this one r will cancel with one of those, and I want to double that. So what happens if I double 500? Okay, so would everybody agree that I'm going to end up with 2 pi r squared plus 1,000 over r? Okay, this is my surface area. This is what I'm going to go ahead and take the derivative of. Okay. Now, before I go ahead and do that, I'm going to go ahead and rewrite it. But is everybody okay with how I got to this point? Any questions on anything? Okay. Now, if I know that I'm going to have to take the derivative of this surface area, I'm going to write it in a way that's easier for me to do that. So 2 pi r squared, but instead of having 1,000 over r, I'm going to say 1,000 r to the negative 1. Because remember, in order to make a negative power positive, you take the reciprocal, but that rule is reversible. Okay. Any questions on that? All right. Well, let's go ahead and take the derivative of the area in terms of the radius. Okay. So how does the power rule work again? I always forget. Okay. So can anybody tell me what would the derivative of 2 pi r squared be? It's just 4 pi r. There you go. So the same thing over here, I'm going to multiply the -1 by the 1,000. So that's a minus 1,000. R to the what? -2. So there's the derivative. Okay. Now, in order to find those maximums, those minimums that we're talking about, what do I set the derivative equal to? What is it? 0. There we go. Those are the only locations where the tangent line is horizontal. So I'm going to set this equal to 0. If I now solve this equation, 4 pi r minus 1,000 r to the -2 equals 0 for r, I've got exactly what I need. Okay, I can find everything I want. Now, there is a way you can definitely go ahead and solve this by hand. Okay, but what's one thing that I've really been pushing? The calculator. Okay, so why don't we go ahead and take this whole equation, let's plug it in the calculator and let's see what we get. Okay, so 4 pi r, 4 pi r minus, and I'll go ahead and do this. Okay. Okay, so menu, I'm going to use numerical solve because it is an equation. So 4 pi r, I'm just going to change it to x. Okay, minus, now I'm going to go ahead and put it as a fraction. So I'm going to say 1,000 over x because that's equivalent, right? I'm going to set this equal to 0. Now remember, when you're using numerical solve, you have to do what? Did I make a mistake? Oh, it is x squared. It is x squared. I'm sorry. I was just saying if you were paying attention. And obviously you were. Okay. I got to keep you folks on your toes. There you go. Yeah. All right. So at the end now, I have to put comma and then what? The variable. So I have to tell the calculator what to solve for. Okay. So in this case, x just represents the radius. So I push enter. So the radius is about 4.3 centimeters. Okay. So right there. So I'm going to come back over here. Okay, so the radius is about 4.3 centimeters. Okay. Now there is something else. We found the radius. Now it doesn't tell me to find what that surface area is, but I should probably go ahead and find what? Let's go ahead and find the height. Okay, so I'm just going to use this formula right here because don't I already have it solved for the height? Okay, so I'm going to plug 4.3 into there. Let's see what we get. Come on back over to the calculator. So control divide. 500 divided by, what was it, pi r squared? Let me make sure I got that right. Pi r squared. So that would be pi times 4.3 squared. Okay. So the height should be about 8.6 centimeters. Okay. So those dimensions will give me the minimum surface area. Okay. Questions? Okay. Had anybody had the opportunity to look at those? Okay. If you haven't, really good idea. Take a few minutes. Choose one problem. Okay. Choose one problem and see if you can work your way through it. If you can, fantastic, because this gives you a lot of practice on some different concepts that we've talked about. Okay. Is there another one you'd like to do? Number 3? Okay. Let's take a look at number 3. Okay. All right. So it says a vegetable garden. I can dig it. Definitely get to the root of this problem. Okay. Is in the shape of a rectangle. The garden is surrounded by 100 meters of fencing. If the width of the garden is X meters, find an expression for the length. Okay, so let's go ahead and come up with a figure here to kind of help us out. So we have a rectangular garden. Let's say that right there. Okay. Then it goes on to say that the width is x. Now, what we know about a rectangle is that opposite sides are what? Equal. Okay. So we have two lengths for x, so that means that over the widths are x, so the length, we'll just go ahead and say L. And I mean, you can use whatever variable you want. Okay. And I'm just going to go ahead and use L for length. So how is this going to help me come up with an equation where I can start? Like, what's one bit of information that they give me here? The perimeter. We know that the sum of the four sides has got to equal 100. So x plus L plus x plus L, that's going to give me 2x plus 2L is equal to 100. Now it says if the width is x meters, which you already know, find an expression for the length. So all I want to do is solve this for the length, right? Okay, so what would I do? How would I start to get L isolated? Okay, let's subtract that 2x over. So 2L is equal to 100 minus 2x. And one more step. Divide through by 2. So L is equal to 50 minus x. Everybody agree? Okay. So why don't I go back over here to my figure, and I'm going to go ahead and replace these with 50 minus x. Are we talking meters? Yes. Okay. So this is 50 minus x meters, and this is 50 minus x meters as well. Okay, so we have A taken care of. We found our expression. But now it says, show that the area of the garden is that. And this is not uncommon in these types of problems. They might really direct you exactly where to go. Well, how do I find the area of a rectangle? Length times width. So in this case, the area would have originally been LX, right? But see, these problems are always going to be progressive. They're going to have you using values and expressions that you previously found. If I know that L is actually 50 minus x, well, then the area becomes x times 50 minus x. And see, that's exactly what they were wanting me to show. Is everybody okay with that? Okay, so part B is done. Part C, what does that mean? dA over dx. Find the derivative of the area in terms of x. Now, before we do that, why don't we go ahead and simplify this? Let's distribute, so that would be 50x minus x squared. Okay. So let's see here. The derivative of the area in terms of x. So somebody help me out the whole expression. What is the derivative of 50x minus x squared? 50 minus 2x. Perfect. Okay. Everybody's okay with how I got that? All right. So C is done. Now in part D, find the maximum area and the dimensions of the garden at this point. So there's that word again, maximum. Okay. What am I going to do with this derivative to help me find that? We're going to set it equal to 0. 50 minus 2x is equal to 0. So let's see, negative 2x is equal to negative 50. So x would equal what? 25. Okay. Now see, I can go ahead and start to work backwards. But before we even finish the problem up, think about how similar the steps were for this problem than it was for number 1. Okay, essentially we had two equations. In this case, it was area and perimeter. We substituted part of one into the other. We took the derivative, set it equal to 0. Okay. So now let's take a look here. If I'm going to come back, if x is 25, okay, what's 50 minus 25? Yeah, 25. So we did say it was a rectangle. I mean, are they still correct? Yeah, because a square is a rectangle, but a rectangle can't be a square. So it looks like the maximum area is going to come from a square garden. Okay. So how would I find that maximum area? What would I do? We know the dimensions are 25 by 25 meters. What's the area that we're looking for? What's 25 times 25? 625. There we go. Okay. If there were definitely any problems that I would look at prior to the paper exam, besides the reviews, absolutely this one right here. Okay. All right. Now, only the first three were shown on this slide. We still have these other two right here. Would you like to try some, on your own, and then we can come back to these later? Do we want to go ahead and try another one together? What are we thinking? You want to try one more together? Which one? Number 5. So a rectangular piece of card measures 20 centimeters by 24 centimeters. Equal squares of side X are cut out of each corner. The rest of the card is folded up to make a box. Okay, so find the volume of the box in terms of X. Find the volume of X for which the volume is the maximum, and then find that maximum volume. Okay, so I'm going to go ahead and get this started, and then I want to see if you folks can walk me through this. So let me get a square here. Okay. So what it's saying is that at the corners, we're going to go ahead and cut out these smaller squares, and the lengths of these are going to be X. Okay. So imagine if these 4 squares disappeared. Well, your piece of cardboard would look like a big plus symbol, right? Well, what if we then folded those tabs up and we gave ourselves a box? Okay, so it's going to look something like this. There we go. Not the best, but we got it. Okay, so we know the height of the box is going to be X. In this case, what are we talking about? X centimeters. So what we need to go ahead and do is figure out what are the edge lengths here and here, and then we can go ahead and take care of A. All right. So why don't you take about 30 seconds to 45 seconds, figure out what those dimensions would be, and see if you can answer part A. Yes. Yeah, go for it. Does anyone think they could give me one of the base edge lengths in terms of X? Okay, one of them would be 20 minus 2X. Okay. So what would the other one be? 24 minus 2x. Okay, so how did we get that? If I go ahead and take a look, let's say that this original piece of cardboard right here, this was the 20 centimeters. Let's say this one is the 24 centimeters. Okay. Well, remember, we're cutting away x, so we're only looking at this length right here. So if the whole length is 24, but I want this smaller length, well, I'm subtracting x, that's where the minus 2x comes from. And then the same idea applies to this base edge right here. Okay, so how do we find the volume of an object? Or in this case, a box. Length times width times height. So x times 24 minus 2x times 20 minus 2x. So you should have ended up with a volume equal to 4x cubed minus 88x squared, and then plus 480x. And of course, that's going to be centimeters cubed. So that's if you multiply x times 24 minus 2x times 20 minus 2x. Okay. All right. Okay, now here's where the other part comes in. Find the value of x for which the volume is a maximum, and find the maximum volume. Okay, what would I do with this formula here, this function? I'm going to find the derivative and do what? Set it equal to 0. That's what's going to allow me to solve the problem. Okay, so what I'm going to do now, I'm going to give you the opportunity to try that. I'm going to go ahead and tell you that when you solve for x, you should be getting about 3.62 centimeters. Okay, and then using 3.62, you should be getting a volume of about 774.17 cubic centimeters. Okay. So go ahead and try that at some point. See if you get those answers. If you do, that is fantastic. If not, definitely come in or, ask myself or Mr. Gonzalez when you see him next time. Okay. All right. And who knows, maybe tomorrow we did what? Numbers 1, 3, and 5? Maybe tomorrow we can come in and start with 2 and 4? Yeah? Okay. Maybe somebody can come on up and show me how to work them? I didn't hear a yeah on that one. Yeah. Somebody said it. Somebody said it. It counts. Okay. All right. So while you folks are thinking about that, let me go ahead and at least introduce the trapezoidal rule to you. Okay. The trapezoidal rule. So you already know that you can find the exact area under a curve using definite integrals. That is the area between the function f of x and the x-axis between two values of x is this right here. Okay. So we've got accustomed, hopefully, to putting that in the calculator, letting the calculator work that out for us. However, sometimes you may not be given the equation, or you won't have the tools to integrate it. So what if they just give you the graph, or what if they just give you a table? Or worse yet, if they do give you the function, what if it's one that the power rule just won't integrate? Okay, so we have to have another way to go ahead and find it. Well, integrals are already technically using infinitely thin rectangles, and estimates for these three, we're going to show this using rectangles and trapezoids. Okay. So let's say we have these three right here. So the first one, A, B, and C. We're going to compare the areas found. Now you'll notice in part A, they've already set up the definite integral for us. So the integral from 1 to 3 below this curve, 2x squared plus 5. All right. All I need to do to plug this in the calculator and get that area, it's already set up for me. So let's see here. I'm going to go, whoop, that did not let me do that. So I'm going to have to come back over here 1 second. Okay, so let me hit that mouse again. All right. So I'm going to go right here between 9 and the open catalog. The one I'm looking for, the definite integral, is already highlighted. Okay. So we have the lower value of 1, the upper value of 3, and what was the curve again? It was 2x squared plus 5. Okay, so 2x squared plus 5. Okay, and then I'm going to go ahead and put x right here. All right. So who can help me out with this? What should I get when I push enter? How many square units? $27.3. There we go. So I'll come back over here, and I should probably go ahead and push enter. Okay, 27.3. Okay, so 27.3 repeating square units. Now that is the exact area of the shaded region below that curve between 1 and 3. Now let's say we didn't know what the function was. Okay, the previous paragraph was telling us that we have a couple of different ways to look at this. We can go ahead and measure it using rectangles, or we can go ahead and do this with trapezoids. And just by visually looking at it, which one's going to give me a better approximation? The trapezoids, because if you take a look at the rectangles, you'll notice you're going to have all this empty space right here that you're not finding. Now, there is going to be an overestimate for the trapezoids. It's going to go above that curve just a tiny little bit, but it's going to be insignificant compared to the loss you're going to get on the other ones. Okay, so let's go ahead and fill this in. Let's see what we got here. Now, the area of a rectangle is, of course, length times width. Okay, so in this case, we're using width and height. Okay, so the width is going to be the increment from your one x value to the next. Okay, so how wide is each of these rectangles going to be? Okay, so that's just one. That's just one right here. So how do you think I can figure out the height for each of these? What would I have to do? If I know that the height of the rectangle touches the curve, that function, when x equals 1, what can I do with that 1? We can plug it in. There you go. So what is 2 times 1 squared plus 5? 7. So the fact that this point right here has a coordinate of 1, 7, I know that the height is 7 units, the width is 1, so this first one has to have an area of 7 square units. Okay, and see, now I'm just going to continue to work my way along. Now, of course, the more rectangles you use, the more approximate your area is going to be. Okay, so how can I figure out the height of the second rectangle? Yeah, plug it in. In fact, plug what in? Now, would I want to plug in 2 or 3? I'd want to plug in 2 because, see, that height touches the curve. Okay. Now, I could go ahead and plug in 3, but it would give me this point right here, and that would give me a much higher value than I'm looking for. Is everybody okay with that? Okay. So let's go ahead and plug in 2. So 2 times 2 squared plus 5. So what am I looking at here? Looks like the height is 13. There we go. So 13 times 1 is 13. What is 13 plus 7? 20. So that is definitely much lower than the value we should be getting. Okay, what you're going to find with the rectangles, if you're doing it in this fashion, it's going to be an underestimation. In this case, it's a pretty severe underestimation. But let's go ahead and find part C, the trapezoids here. Okay, now you'll notice the formulas have been changed slightly. Forget about those right there, what it says on screen. Does anybody remember the original formula for finding the area A of a trapezoid? There you go. 1/2 the height times the sum of the bases. Now, when you're talking about the bases, those are the sides of the figure that are opposite one another. They're parallel. The height is the perpendicular distance between the two. Okay, so in this case right here, look at this trapezoid. right here. So this would be, for example, base 1. This would be base 2, if I can write a 2 right there. And then the height, remember, that's the perpendicular distance between them. Okay. So for this one, we actually already know everything we need to. Let me go ahead and pull this over here. We already know that that first base, because of what we did previously, well, wouldn't that be 7? What would the length of the other base be? So remember, this right here is this one, so that would be 13. And we know that the increment between them is just 1. Okay. They just went ahead and changed it here, so instead of the bases, that represents the heights that we're looking at. The width is the horizontal distance between them. So the fact that they're using different variables, don't let that throw you off at all. Okay. So for this one right here, I want to take half the height, well, 1, or excuse me, in this case, again, the height's there. Okay. Times the sum of the bases, so 7 plus 13. So what's half of 20? 10. So this first one gave me 10 square units. Now we want to go ahead and do the exact same thing to the other one. Okay, so I'm looking for this trapezoid right here. Okay, now we already know that the first height is 13. Okay, we know that this is 1, but we don't have that 3 right there. So I do need to do what at this point? How do I find this other length? How did we find the other lengths previously? We plugged it in. There you go. So now I do want to go ahead and plug in that 3. So let's see here. 2 times 3 squared plus 5. Okay, so 3 squared, 9 times 2. Okay, 18 plus 5 is 23. Okay, so the height that I'm looking for here is 23. All right. I have everything I need to go ahead and find that area. Okay, so this is 1/2. The height 1 times 13 plus 23. Okay, so let's see, what's the 13 plus 23? 36, and what's half of that? 18. So that's 18 square units. So now if I take the sum, the area of that trapezoid plus the area of that trapezoid, I'm going to get 28 square units. Now see, when you're using trapezoids, it's always going to be an overestimation. But how close were we? 27.3 versus 28, we were still definitely pretty close, right? So this is going to be like a backup plan in case we don't know how to integrate a function, or maybe we're not given that. That's going to be our goal. We want to go ahead and use trapezoids to find the area. Avery? Well, it depends on your increments, and they're not always going to be 1. I mean, the consistent increments between your horizontals, in this case it'd be the height of your trapezoids, the smaller you make those, the closer the overall sum's going to get. So it really just depends. I mean, for me, you've seen how I've graded over the past, close to 9 months. If you're in the ballpark, I'm definitely going to go ahead and count it. The only thing I'm concerned about is how will the IB grader, how will he or she do that when they get your paper in front of you? I mean, what I would say, and this is always a good plan, if you're ever not sure, show stuff like this. Okay? What am I referring to there? Yeah, show your work. The more work you show, even if the answer is wrong or they won't accept it for whatever reason, the more likely you're still going to get at least credit on that. Okay. All right, but that's basically our idea going into this lesson. Any questions? So it's not too bad, right? Essentially what you're doing here is you're going to be finding the areas of trapezoids over and over and over again to get a whole sum. Okay. All right. It's a trapezoid. I had to say, Admiral Akbar. That's our truck. I was like, it's pretty cool, right? Okay. All right. I'm going to go ahead and stop there because I'm willing to bet that, I like Mr. Gonzalez. I know he's pretty cool. I just don't know that he's going to have the same sense of humor as I do. So I want to go ahead and get a few jokes out there. I would say that. I heard a good joke the other day. Did you know, this is a true fact, that trees are able to poop? Why do you think we have number 2 pencils? Number 2 pencils. Number 2 is also another word. I would make another joke, but it'd be pretty crappy. So I'm gonna stop while I'm ahead.